Hello. So in the previous video, we saw some examples of voltage-controlled voltage sources, or in other words, voltage amplifiers, specifically the inverting, non-inverting, and voltage follower. And in this video, we're going to talk about current sources, or voltage-controlled current sources in this case, which we can also term transconductance amplifiers. And we're going to see a couple of different configurations for transconductance amplifiers using op-amps, and we're going to use the ideal op-amp model to analyze these circuits again. So voltage-controlled current sources, also referred to as transconductance amplifier. And we're going to take a look at examples that contain floating loads. And what we mean by floating loads is that none of the load terminals are connected to ground. Then we're also going to see some examples of grounded load transconductance amplifier. But for the first one, we're going to see the floating load inverting transconductance amplifier, or VCIS. And it's very simple. Structurally, it's very similar to the inverting amplifier, except now our feedback resistor becomes the load resistor. So let's see how that works. So in this case, we're doing the inverting, and so that means our input signal is applied at the inverting terminal, at the negative terminal of the op-amp. I'm going to call this R1. And then our load resistor, so this will be basically the circuit with the positive input grounded. Our load resistor is going to be connected between the negative input terminal and the output, and that's why it's termed a floating load. Not one of the terminals is connected to ground. And so this is my RL. And there's going to be, obviously, some voltage that develops at the output, as well as some current that's going to flow through the load. And that's going to be the output current. I've referred to it as IL, but I might as well call it I out, since that's the output current, the current that's flowing through the load. Now notice that in this case, there's only going to be any current flowing through the load when there is a load connected. If the load is disconnected, the circuit becomes open loop, and therefore the output of the op-amp will just rail. There will be no current flowing across the feedback path. If we wanted to avoid that scenario, we could always connect some resistor in parallel with the load of value sufficiently large that whenever there is a load connected, most of the current will flow through the load. And so essentially, when there is a load connected, the parallel combination will be approximately equal to the load resistor. But let's just analyze the circuit as it is like this. And so we have some current flowing through resistor R1. I'm going to call it the input current. And we know that because there is a voltage V in applied. And then we know that the negative input terminal is sitting at the same voltage as the positive input terminal, since this is a negative feedback configuration. And therefore, this terminal is sitting at ground, or 0 volts. And so if there is a voltage across resistor R1, there must be a current flowing through resistor R1 by Ohm's law. And that current, again by Ohm's law, is going to be equal to the voltage across that resistor V in minus 0, or just V in divided by the resistance R1. Now, by Kirchhoff current law, we know that at the particular node, the negative or the inverting input terminal, the sum of the currents entering that node must equal the sum of the currents leaving the node. If we make the ideal op-amp assumption that the current going into the inverting terminal of the op-amp, into the input terminal of the op-amp, is equal to 0, then I have that my I out must be equal to my I in, because some of the currents leaving the terminal must equal some of the currents entering the terminal. Therefore, I can write I in is equal to I out, and we've already determined that I in was equal to V in over R1, and therefore I out is the same has the same value. And from here, I can calculate my gain term for the circuit. In the case of a transconductance amplifier, the gain term is the transconductance of the circuit, or the ratio of the output current to the input voltage. And we can see that it is equal to 1 over R1. To maintain linear operation, if we wanted to know what are the requirements for linear operation, we will have that V out needs to be less than the saturation voltage. And since V out, we can see from the way the circuit is configured, it's going to be equal to RL times I out, or actually negative RL times I out, since the I out current is flowing in the direction from 0 towards V out. We will have, this is I out times RL, that needs to be less than V sat. And again, we can relate I out to V in, because we know I out is equal to V in divided by R1, and so I could still rewrite this as V in times RL divided by R1 must be less than V sat. And so that essentially gives me the range of input voltages V in for which the circuit operates linearly. I'm going to highlight the linear operation as well as the expression for the transconductance of the circuit. A simple variation of this circuit will be the floating load non-inverting VCIS, which will essentially be the same circuit, except now the input voltage will be applied to the non-inverting input terminal. But everything else is the same. R1 is still connected there. We still have our load between the output and the negative input terminal, so basically connected in the feedback path, RL. And that is V in. And in this case, I have my current. This will be V out. My output current, I know that it's going to be flowing in that direction, I out. And the reason why I know that is because my output current is going to be equal to the current I1 flowing through resistor R1. And since the voltage at the negative input terminal is going to be V in, assuming V in is a positive value, the current is going to flow from the voltage that is most positive towards ground through resistor R1. And so I know that's the direction of the current. And since there is no current flowing into the input terminal of the op-amp, that current must be all coming from the feedback path, so it must be equal to I out. Let's go ahead and analyze the circuit. Similarly to what we did before, we can use Ohm's law to come up with an expression for I in, which is just going to be same thing as before, V in minus 0 divided by R1. From KCL, we know that I in must be equal to, or I1 I called it in this case, must be equal to I out. And so I out is also V in over R1. And therefore my transconductance, which is the ratio of I out to V in, is again equal to 1 over R1. So notice same expression as before. The only difference is, notice the direction of the current I out. So in the case of the inverting VCIS, it is flowing into the output terminal of the op-amp, and in the case of the non-inverting VCIS, the current is flowing out of the output terminal of the op-amp. Okay, so opposite directions of current, but of of current, but overall the transconductance in absolute terms is the same. If we wanted to know the conditions for linear operation, again with an op-amp, the condition for it to be operating in the linear region, or for any op-amp based circuit, is that the output of the op-amp be less than the saturation voltage, both on the negative and the positive side. Normally we express this as the absolute value of V out being less than the saturation voltage. And again, this is assuming that the saturation voltage is symmetrical on both sides, but it should be easy to modify the calculation if we had a non-symmetrical case for positive and negative saturation voltages. And the V out we can see in this case is going to be equal to I out times R1 plus RL. That must be less than the saturation voltage. And I out, again, I can relate to my V in through the equation that I came up with earlier. And so this is going to be V in times R1 plus RL divided by R1 less than V sat, or essentially V in times 1 plus RL over R1 must be less than V sat. And so that will be the condition for linear operation, the range of input voltages that are going to result in linear operation of the circuit for the floating load non-inverting VCIS. Thank you.